So this lesson is called Solving Quadratic Equations by Taking Square Roots. And it's actually going to be a little bit from section 4.5 and a little bit from 4.7, which is called Completing the Square. Because in the end, you're able to take square roots in both of those. So some of this is just to remind ourselves, now that we're going to be taking square roots, some of the properties of working with square roots you need to refresh yourself on. You've had this before. If you don't understand what you see on the left, then look at the example on the right and see. You know, a product property can go both ways. You know, it could either be that if you have the square root of 18, you say, well, 18 is not a perfect square. Does 18 have any factors that are perfect squares? And then because of your knowledge of multiplication tables, you say, sure, 9. So you split it up into two radicals. The square root of 9 times the square root of 2. That's a product property. Sometimes we use it to break up a radical. Sometimes we use it to put radicals together. Okay. And then there's also a quotient property, which is if you have a quotient, a radical of a quotient can be split up into a quotient of radicals. And if it helps you to simplify one part of it, then by all means you do it. You know, look at their example here, the square root of 2 over 25. If they break it into two radicals, the denominator to the square root of 25, that simplifies. And so you can simplify it. Now the square root of 2, you can't do anything with that. So we leave an unresolved square root in the numerator. So product properties and quotient properties. So here's some examples. On the letter A, the square root of 80. Again, you have to think, is 80 a perfect square? And if you know your multiplication tables, you say, no. I mean, multiplication tables, perfect squares. Do you know the perfect squares? Right? Is 80 one of them? No. So you say, okay, if 80 is not a perfect square, does it have any factors that are? Right? And you could just start going down, think of the perfect squares. The perfect squares are, I won't use 1, but 4, 9, 16, 25, 36, 49, 64, and 81 would be more than 80. But you just say, are any of those factors of 80? And the truth is, yeah, 4 is, and 16. You always want to take the biggest one because you want the most simplification. So you can see what they've done there. They said, okay, well, let's break 80 into 16 times 5. Because then we can simplify the square root of 16. We get the most simplification. 4 root 5. Maybe when you did this in the past, you used factor trees or something like that. I don't know. And if that works for you, by all means, do a factor tree. Notice on the letter B, they're actually kind of going the opposite direction. Right? They've got the product of radicals, the square root of 6 times square root of 21. Neither one of those is a perfect square. Neither one of those has factors that are perfect squares. However, if you notice, both of them have a common factor. What is it? 3, right? So if you put it all together in one radical, now you're going to have a 3 times 3 inside one radical, and you will be able to simplify. So they put it together into 6 times 21, the square root of 126, and then factored the 9 out of that. That's 9 times 14. And you get the square root 3 times the square root of 14. Now make sure when you simplify radicals that, you know, when you simplify that square root of 9 and get 3, there's no more radical. Don't write a radical sign over the top of it. You know, you got rid of that by taking the square root of 9. You know, the letter C, you know, if you know your perfect squares, that's pretty straightforward. The letter D, same thing, that you recognize 7 is not going to be simplifiable. You can live with that in the numerator. You can't live with that in the denominator, but you can live with that in the numerator. We're going to talk about the denominator in a minute. So go ahead and try to simplify these as a you try. Right, so this, the number 1 was the square root of 9 times the square root of 3, which is 3 root 3. The square root of 98, the square root of 49 times the square root of 2, which is 7 root 2. And the others, those are actually, I think, easier. You know, they're just 3/8 and the square root of 15 divided by 2. I mean, does the square root of 15 simplify? You know, again, you just think, is it a perfect square? No, it doesn't have any factors that are perfect squares. 1, 3, 5, 15. No, no. So you're done. So if we have a square root in the denominator, then we need to get rid of it. And if it simplifies like the last slide, that's great. Then you don't have to do anything special. But if you have an unsimplified square root, like this letter A, right, the square root of 5 over the square root of 2, you have to do something that's called rationalizing the denominator. You've done this already. Okay, you did this, at the very least you did this in geometry when you did special right triangles. If you remember, in a special right triangle, let's say a 45, 45, 90, remember that? The formula for the sides were x, x, and x root 2. And if, for example, they gave you a triangle and they said it was 45, 45, 90, and that you knew the hypotenuse was 5, then you would have to solve for the x by saying x times the square root of 2 equals 5. And if x times the square root of 2 equals 5, then x equals 5 divided by the square root of 2. And then you had to rationalize the denominator. So you did this. I don't know if you remember doing this, but you did do this. But what you do to rationalize the denominator when all you have in the denominator is one square root, right, like the square root of 2, that's like this first line right here. What do you multiply by? The same thing. So if I want to rationalize the denominator when it's got the square root of 2 in it, I multiply times the square root of 2. But if I multiply the denominator, I got to multiply the numerator, so that overall I'm multiplying by 1. Now what is the square root of 2 times the square root of 2? It's the square root of 4, which is 2. The square root of 2 times the square root of 2 is 2. What's the square root of 3 times the square root of 3? 3. The square root of 7 times the square root of 7? 7. That's always the way it works, right? So that's, if you have a monomial radical in the denominator, you multiply by that number divided by itself. If you have what's called a binomial radical expression, binomial means two terms. Right? At least one of the terms has a radical. Could be both. That would work too. Then you have to multiply not by the same thing. You don't multiply by 7 plus the square root of 2. You multiply by 7 minus the square root of 2. That's called conjugate. Right? If you start out with the binomial radical expression that's got a plus in between the two terms, then you switch the plus to a minus and multiply by that. If you start out with a minus between the two terms, then you multiply by the plus. I mean, notice what happens. I'm looking at their example on the bottom here, right? When you multiply 7 plus the square root of 2 times 7 minus the square root of 2, the 7 times, it's a FOIL. The 7 times 7 is 49. The 7 times negative root 2 is minus 7 root 2. 7 times positive root 2 is plus 7 root 2. So those last two terms cancel. And the square root of 2 times the square root of 2 is 2. So by multiplying by what we call the conjugate, you get rid of all the radicals in the denominator. Right? It's okay to have a radical you can't simplify in the numerator. It's just not okay to have it in the denominator. And we have to do that a little in this class, not a lot, but it's presented at the beginning, and we end up doing it more like later in the class, and might as well just get it out of the way now. So we're not going to do all these. I don't want you to multiply them all. I just want you to tell me what would you multiply by to rationalize the denominator for all four of these, okay? Just using that chart on the previous slide, what would you multiply to rationalize denominator? Again, what would I multiply the first fraction by? It's only got one term in the denominator. It's the square root of 5. So what would I multiply by? The square root of 5 divided by the square root of 5. What about the number 10? Yeah, there's a couple answers here, right? You could say, let's multiply by the square root of 8 divided by the square root of 8. It's whatever the denominator is divided by itself. But truthfully, the square root of 8 could have been simplified. You know, we could have written that like this. We could have written 9 divided by 2 root 2, because that's what the square root of 8 is. And then what would we multiply by? The square root of 2 over the square root of 2. What's that? No. Oh, yeah, you're right. There was a square root over the 9, and then that would simplify, wouldn't it? Okay, what do I multiply by in the number 13 to rationalize denominator? All right, go back to the chart. All right, if you've got a minus the square root of b, then you're going to multiply by a plus the square root of b. So what will that look like? 7 minus the square root of 5, so we multiply by 7 plus times 7 plus the square root of 5. What about the last one? 4 minus the square root of 11. 4 minus the square root of 11. What's that? No, you would have to simplify it. We're not going to do that right now. You know, I just went through this last class, and we had a lot to cram in there. It was a little bit too much, I thought. So if I feel like I'm rushing, if it seems like I'm rushing a little bit, I am a little bit. Yeah.
So don't worry about simplifying.
Well, you should try to simplify it. If you get a problem to do it in the homework, go ahead and, after you set it up like that, then go ahead and try to simplify it. You know, it'll be a FOIL in the denominator and a distributive property in the numerator. Actually, this is going to relate to something we do next class, which next class we introduce complex numbers, meaning complex numbers are real numbers and imaginary numbers. It involves the letter I. We define I as the square root of -1, and we have a thing called complex conjugates then. So, and we end up doing exactly the same thing with those. So that's why it's not a bad thing to get out. So now we can get to the, okay, now we're ready to solve a quadratic equation by taking square roots. Well, if you remember, the reason that we had to factor our quadratic expressions before was because we had x in more than one term, and they weren't like terms, and you couldn't put them together so that they would isolate the x. But if you don't have the x to the first term, what you call the linear term, you can isolate the x term, right? You can isolate the x squared, right? Because by isolating the x squared here, then you will be isolating the variable. And then once you've isolated it, you can take the square root of both sides. So we don't really need to go through all that factoring process because the x is only in one term. So isolate the x squared, take the square root of both sides. So how do they, in this problem right here, they rewrite the problem here on the first line. Okay, what are they doing to go from here to here? Right, they subtract 5. To isolate the x squared, they subtract 5. Right, minus 5. What do they do to go from here to here? divide by 3. Okay, once you've isolated, take the square root of both sides. Okay. So if I take the square root of x squared, I get x. If I take the square root of 12, I have to write plus or minus. Right? You have to include the plus or the minus. I mean, and this can get complicated, but I mean, you know that 4 times 4 is 16, but negative 4 times negative 4 is also 16. So in that sense, you take the square root of 16, you really get plus or minus 4. Now, if you are solving an equation which has a radical in it, right? If I had something like the square root of 16 plus x equals 10, something like that, I can assume they mean positive 4. Right? When you're given a square root, you assume they mean what's called the principal square root, which is the positive one. But when you take the square root, because you're solving an equation, you have to include both. Right? That's the difference. So always include this plus or minus, which is right there. And then, 12 is not a perfect square, but does it have a factor which is a perfect square? Yes. So they break it into a square root of 4 times the square root of 3. Now it's plus or minus 2 root 3. So it's basically isolate x squared, then take square root. Remember the plus or minus. And again, we expect when we solve a quadratic that we're going to get 2 answers. If you didn't have a plus or minus, you didn't get 2 answers. Okay. Emily, you okay? You okay? Okay. So go ahead and try to solve those two. It's fun. Okay, so what do you do on the first one to isolate the radical? Divide by 5. Right? X squared equals 16. Take the square root of both sides. X equals plus or minus 4. What do I do to isolate the square term on the second one? Add 7. It's not an x. Z squared equals 36. Take the square root of both sides. Z equals plus or minus 6. So it would seem like that has kind of limited applicability. I mean, it has to be when you don't have a linear term there that you could isolate the squared term, and that would be solving. But actually, we can use this even when there's a linear term by doing something that we call completing the square. And if you look at this problem here, when we solved equations in the last lesson, we wouldn't have allowed to have anything other than 0 on the right-hand side. Well, this time we do, right? We have a number on the right-hand side. But notice the quadratic, which is on the left of the equal sign. That's a perfect square trinomial, right? The factors of 16 that add up to -8 are -4 and -4. So that's x minus 4 squared equals 25. Okay, because it was a perfect square trinomial, you've isolated the x in one spot. So as long as you've still solved for the squared term, which in this case is x minus 4 squared, now you take the square root of both sides. Right? So in this case, I'm going to get x minus 4 equals plus or minus 5. Don't forget that. But I have one more step. Because I have x minus 4 on the left, to solve for x I have to add 4. So that's what you can do when what's on the left hand side is a perfect square trinomial. So try to do the same thing with that. So what was the perfect square trinomial on the left of the first one? How does this factor? X plus 3 squared. Okay, now that we've solved for the squared term, what do? Take the square root of both sides. So now we get x plus 3 equals what? Plus or minus 6. But you still haven't solved for x. Last step, subtract 3. So it's x equals negative 3 plus or minus 6. Which you don't have to leave it like that. I mean, we can calculate that, right? That's negative 3 plus 6 equals 3. Negative 3 minus 6 is negative 9. Two answers. How about the one on the right? How did it factor? X minus 5 squared equals 1. So x minus 5 equals plus or minus 1. Take square root. Add 5. X equals 5 plus or minus 1, which is 6 and 4. Today? No, you're not solving any equations on it, it's just factoring. Okay, the thing is that we don't often get perfect square trinomials to deal with. But you can make a perfect square trinomial by doing what we call complete the square. Right? Completing the square means if you just take the x squared term and the x term and figure out what would you add to make it a perfect square. There's a 3 steps here. Right? Step 1, find half of the middle coefficient. So in this problem, x squared plus 16x. 16 divided by 2 is 8. That's the first step. Second step, square it. Square that number. 8 squared equals 64. Okay, that is the value of c right there. So then you can replace the c with the 64. Now look at this one right here, which is just the example. How would that factor? What are the factors of 64 that add up to 16? 8 and 8. So you just made a perfect square trinomial. By picking the right number to go in that position, you made a perfect square trinomial so that we could use this method. Now, completing the square is something you end up having to do in this class. And, you know, if you go on to math analysis, you'll have to do it there. You'll do it in calculus. I mean, it comes up a lot. And most of the time, teachers are frustrated because it doesn't seem students know it very well. But it's not going to go away. If you stay on that track, you're going to end up doing this again. So I'm going to skip over the next couple slides because I don't think they added anything to this. So I'm going to do this one. Okay. Again, what are the steps to find what number I'm going to add into the third position? Step 1 was
Take
half of the middle term. 14 over 2 equals 7. Okay, step 2. 7 squared equals 49. So that's what goes there. X squared plus 14x plus 49. And it should be at that point, you recognize the perfect square, right? The factors of 49 that add up to 14, 7 and 7. Okay. Okay, try to do the next one, the number 5. So what, in the number 5, what was the C? 121, right? You take half of 22 and you square it. So now we have x squared plus 22x plus 121, which is x plus 11 squared. Now the last one, which I'm going to do, it's still the same process. Just what's different about the number 6? What's going to happen when you divide by 2? Then negative is okay, right? Negative really doesn't make any difference. What's that? Yeah, it's going to be a fraction. That's okay. All right, this is what it looks like, right? I take the negative 9, I divide by 2, and then I square it. What does negative 9 have squared as a fraction? What's negative 9 squared? 81 over 4. Good. So that's 81 over 4. Now remember, when you square whatever the half of the middle is, it's positive, no matter what. You're never adding a negative number in that spot, because a square is always positive. All right, so this is what it looks like. X squared minus 9x plus 81 fourths. Now, when that happens, nobody can look at that and just in their mind immediately the factors come to mind, right? What is the perfect square trinomial there? Like we could on the first two, you could see it exactly. But when you have fractions involved, just remember it's half is when you took the half, that's what it is. So when we did 9 over 2, that's what goes inside the parentheses to square it. So you won't think of it as a factoring. You're just going to say, okay, whatever I took the half of, that goes there. Okay. Okay, now we can use this method to solve by taking square roots, right? We can complete the square to make a perfect square trinomial, then take the square root of both sides. This is an example that they've worked out in the book. So generally, you have a square term and you have a linear term and you have a constant term. Put the constant term on the other side. So they subtracted 4 from both sides. Okay, now, looking at just these two terms, x squared minus 12x, what do you need to add to complete the square? Take half of negative 12 and square. Half of negative 12 is negative 6. Negative 6 squared is 36. So you add 36 here to make a perfect square trinomial. But this is an equation now. You can't just add something to one side and not balance it out by doing the same thing to the other side. So when we add 36 on the left, gotta add 36 on the right. And this is the perfect square trinomial, right? X minus 6 squared. And this simplifies, that's 32. But at that point, we've isolated the x in the square term on the left. We're ready to take the square root of both sides. All right, so from this step to this step, take the square root of both sides. Plus or minus the square root of 32, and then because you still had the minus 6 with x, you add 6 to both sides. 6 plus or minus the square root of 32. Now the square root of 32 can be simplified. Right? 32 is not a perfect square, but it has a factor which is a perfect square, 16. So that's what they've done going from this line to this line. So I'm going to do one and you can do the other. So if I follow the steps that we saw on the last slide, what's the first thing that I do on this number 7? Subtract 4 to the other side. X squared plus 6x. And I'm going to leave a space so that I can add a number there. -4. Okay, now I need to complete the square on the left. What number will I add into the third position there? Half of 6 is 3. 3 squared is 9. So I add 9. Okay, now on the left, I have a perfect square trinomial. X plus 3 squared. And on the right, I have 5. Okay, I've isolated the squared term on the left. What's the next step? Caitlin. Take the square root of both sides, right? So what does it look like when I take the square root of the left? The square root of a square is what's inside. And then what does it look like on the right? Plus or minus the square root of 5. Okay, I'm not quite done. What do I have to do? Subtract 3. So x equals -3 plus or minus the square root of 5. Try the number 8. Try to do the same thing that I just did. You have that one to look at. So I'm going to go through this kind of quickly. X squared minus 10x equals -8. Half of -10 is -5. -5 squared is 25. If I add 25 there, I add 25 there. This is x minus 5 squared. This is 17. X minus 5 equals the square root of 7 plus or minus the square root of 17. So x equals 5 plus or minus the square root of 17. So it's in the section, this is coming from the section on completing the square, but it's really solving by taking square roots in the end. It's what we learned in section 4, whatever, 4 or 5. Now there's only one more I need to show you. We don't have much time for it, but if you get a problem like this, right, where a does not equal 1. Now this is not a great example. In fact, I should like make this like a 13 or something like that, so that we don't think we're going to divide out a 2. Right? If you have a number other than 1 for the coefficient for a, the coefficient of the squared term, you need to factor it out, because you can't do this complete the square process unless you have a equals 1. So again, I'm changing this to say minus 13, and now I'm going to go through the process. This is what it would look like. You would go 2n squared minus 4n equals 13. Okay, factor the 2 from the first 2 terms. 2 times n squared minus 2n equals 13. Now complete the square on what's inside the parentheses. Right, don't worry about that 2. What would you add here to complete the square on n squared minus 2n? 1, right? You would divide -2 by 2. You get -1. -1 squared is 1. Okay, now what do you add to the other side? Actually, you add 2, because that the 1 is inside parentheses and it's being multiplied by a 2. So to balance putting a 1 in that position, you got to add 2 to this side. So keep that in mind. So this becomes 2 times n minus 1 squared equals 15. N minus 1 squared equals 15 halves. And from there, you can take the square root of both sides and do all that. But the main thing, just understand that the complete the square process is only when a equals 1. And if a doesn't equal 1, you need to factor that out of the first 2 terms.
What do you do with
This one here, I divided by it.
Oh.
Now it's on the right. I'm not going to finish that because we're really running out of time. I want you to have the quiz start. But just keep that in mind for if you have a coefficient other than 1. So that's our homework.